but with C subscript everywhere. So one thing to notice is that actually, if you will, okay, statement one. If you will increase m, this will also converge to F2. So GMCP converges to F2P. Now, in other words, then m is large enough, then these boundary things, they don't play much role. But what is amazing is that they tend to F2 of P in more subtle fashion than GM did. So GM was just growing, but these guys do certain interlacing. So G1 of C is less than G3 of C, E less than G5, and so on. Then we have F2 of P, and then we have G6C, 4C, and G2C. And that's really great in the sense that it doesn't give you just the lower bound, it just gives you lower and upper bound. Yeah, okay, we have to fact this false because it's not true. Okay, so sure. So this behavior is observed, is true for m less than or equal to 17. So that's reasonable evidence, actually.
But you don't know. It's false for 18.
No, and for 18 it just was too hard for him. Actually, I think it could be computed.
So it could be a good fact, but you don't know that.
We don't know that.
Yeah.
So yes, so it's I don't have any indication that it's wrong. So it was just checked for m up to 17, and that's it. So you can just now take these guys. You can compute them also because for them it's also you can use these things with the corresponding function also be algebraic. There will be just a little bit different transfer matrix. But you can compute them efficiently, and that's how you can bound. And actually, computing up to 17 gives you pretty good accuracy. So, like, it depends on p, but like for p around 1/2, it's like I think 5 digits, 5 correct digits. That's good. For larger p, it's harder. For smaller p, it's better, but it's pretty good. But I have no idea why is it true. I mean, even like combinatorially, it should be something combinatorially understandable, but no idea. Just no idea. And of course I would like to know why. So, and this is it with this approach. And now I will show another one. So maybe I will just erase all what happens here. So keep. Okay, so one reason why this reduction is useful, which I just showed, is that it can help you with computation with strips. Okay, however, you can do it a little bit differently, in the sense that not only this theta m is a constructive thing, theta mn is a very constructive thing. It's polynomial, and you can compute it. And this polynomial, you can compute all. Using again transfer matrix method, whatever it is. So how can we, using this theta mn's, find some approximation to theta? It turns out that we can. So this will be, let's see power series approach. And the main idea will be in the following fact. So let's call theorem. Oh no, I had other fact statements, so let's call the statement. And this is this is my result. 2017. So what you can say is that if you take log of theta of z, and this log is actually what you're interested in. Okay, I'm interested in. So, and then you can say that this is equal to, I will write and then I will explain what this means. Sn 1 plus 2. Okay, so you can get first n minus 1 terms of this log if you know what Sn, Sn minus 2, and so on are. You don't know because you didn't give the definition, but the definition is where Sm is just the following sum of theta and n z, where n plus n is equal. So, and now it is now purely like algebraic inventory. So you can compute these polynomials, and if you compute them for all these sums, then you can sum up somehow and get some part of Taylor expansion for this log. But this is proved fact. This is fine.
So that's a different approach.
Yes.
Answer the same question.
To the same question, compute an f of p.
Yeah.
So
this is more efficient.
This is more efficient for small p's, and the previous one was more efficient for large p's. So they sort of speak complementary. I have a comparison of them. Yes, but actually, so far, previous approach is much better because previous approach, up to that conjecture, gave us lower and upper bounds. This approach, the only what it can give us is part of power series expansion of f of p. And power series expansion, it gives you like approximation, but normally it doesn't give you neither lower nor upper bound. And the thing which happens is the following. So let's, how can we write this f2 of p? Because of some log here and integral here, what happens is that f2 of p starts with some logarithmic term, and then it continues as reasonable power series. So first you have a linear term, this little bit irrational, and then you have this thing. And then what I can do, using some symbolic computation techniques, I can compute this Sn far enough to get like 63 of these BGs.
These are rational numbers?
They are all rational numbers. And what you see is that they all are negative. All these 60 something. So, and now, if you believe that they are all negative, then of course, truncation of this power series gives you an upper bound. Upper? Yeah, upper bound. Upper bound for the final thing. And this is already good. But now, and this is, again, this is not my idea. This is what's mentioned in some other paper, that for physicists, it's natural to write fp in a bit different way. They write it as, okay, the same first two terms. And then you say that around 1, where density is high, you can also use some kind of approximation and say that let's also consider this part. So from purely mathematical standpoint, I have just done nothing. Okay, because this function at 0, it has honest Taylor series expansion. Okay, it's a good function. Actually, it has very very good expansion. It's like 1 over k or so. So what I just did, I just subtracted some rational numbers from all these BGs. Nothing interesting. But what happens is that now, of course, if I can compute 60 BGs, I can compute 60 AGs. And observation is that AGs are positive. And this completes the puzzle, because now, if you take truncation of this power series, then it gives you a lower bound. And that's how we get, again, up to conjecture that these and these two facts are true. After this conjecture, you get lower and upper bound. And again, there is a good, again, it depends on how far can you go in this computation. So I could go up to 60, and for small p, it's very good. For large p, previous approach was better.
So what p is the critical p that these two methods are almost the same?
I think like 0.9. So
Probably for most p, your method is better.
So, okay, if you measure using usual Lebesgue measure, then yes, I suppose that there is certain another measure like of physical interest, and I think it might be different. So I think high density is of certain special interest. But that's again maybe I'm wrong. But that's what I can see from papers. So, but they're kind of complementary. And of course, I mean, that person, he was a physicist, so from his papers I see that he used some like, simple computation things like Penalty-Dilson method and Grobner basis in quite naive fashion. So if he would be a bit more sophisticated than that, I think he could go further. So that's, and maybe, because for these 60 terms, there was like computation, it was on the server for several days, and with 1 terabyte of memory. So it's not on the laptop, and I don't know how did he compute. Maybe he computed on the laptop. Then it's unfair to compete, of course, somehow. But another reason why I wanted to have power series expansion is that I wanted to guess whether there is maybe a nice differential equation that this function satisfies. And in this sense, I have bad news. I don't have any guess. So it's not enough terms to guess something. Maybe I have to guess not differential equation, but something else. But for that, I need physical intuition, which I don't have.
Maybe some change of number.
Yes, maybe I have to exponentiate that to get rid of logarithm, or maybe I have to subtract logarithm, or I don't know. Maybe there is something, another ansatz which will give a result, but maybe not. So I think I have like 2 minutes. Oh no, I have 8 minutes.
Yeah.
Oh, I have 8 minutes. So then maybe I will just say a couple of words about one small trick in this story, which a person liked, and it was. It would be not acceptable in mathematical paper, but it was fine for physics paper. So this equality says that for first n terms, left-hand side coincides with right-hand side. Okay? So, of course, both left-hand side and this part, they are defined after the nth term, but they're just different. The point is that if I consider the difference, so let's just erase that and consider this difference. Okay, so it starts from like z to the n minus 1, and then its coefficients, they can be understood as a solution of some combinatorial problem, like number of polynomials with some properties. So all coefficients, like first coefficient is polynomials with these properties, second coefficient is polynomials with that properties, and so on. I was hardworking enough to work out myself the formula for the first coefficient. From pure combinatorics, it took a long time, and I have 3 different answers, so I didn't know which one is correct. So for the second, I understood that it's feasible, but I will get 10 different answers, and I will spend 2 days. And what happened is that but of course I can run it for several capital N's, and I can generate these differences for different N's. And it turns out that you can just guess formulas for 5 terms after this plus, just guessing as a C-finite sequence. So as something satisfying linear recurrence. So if I did computation honestly, I would get only like 55 terms. With this trick, I get 60 plus epsilon terms. Because of just understanding that the terms after, they diverge by something combinatorially meaningful, and guessing the formula for this combinatorially meaningful. And this was kind of fun to use.
So how many extra terms do you get with this?
5 or 6, I don't remember exactly. So 5 or 6 terms, and this is good because like each 2 terms double my memory requirements for computation. So I saved a couple of servers in that, and that's nice to have.
And you cannot continue this trick even more.
But then I will have, so further you go,
Yeah.
larger the recurrence larger the recurrence is, and after 6, 50 terms which I have from it is not enough. So if I get a little bit more, then I could guess a little bit more, but yeah, not much. But I just like the trick. And yeah, I have a couple of more minutes. I just want to say that all of this work was discussed with Manuel Cowers, who did this seminar. He didn't want to be coffee, but I want to acknowledge his great
And he's speaking
contribution to the project.
And he's speaking next week.
And he's speaking next week, so I think you will have a pleasure of having him here. I'm done. Thank you very much for that.
Questions?
Question on since the theta mn, the original one on the left, so this is a polynomial, right?
Right.
Okay, so do you know whether people looked at the zeros in the complex plane, complex Z?
They definitely did. So okay, well, I mean, they did either for theta mn or for theta. I think for both. I think they did. But I just cannot cite you results.
Now, the reason why I'm asking is because, not in this exact same setup, but there's this famous Young circle theorem, right? They looked at such a theta, which also was a polynomial, right? And so turned out that all the zeros were lying on a circle in the complex plane. And when you let then m and n go to infinity, right? So then they were pinching up
the whole
thing, and that causes a phase transition, and that's actually connected to my earlier question. Are you sure that this thing is actually convex originally? Also, because otherwise the Legendre transforms may miss a certain piece. So that's all connected.
Yes, I mean, so I have read many papers on the subject without full understanding them, unfortunately. So, and there were discussions of zeros. I don't think that they have such a precise result like as a circle, but they have some bounds, I think, like they lie inside. So I think like it's also, by some reasons, valuable to bound the region where all these zeros lie. So, but however, there is no phase transition in this model.
There's no phase transition?
No phase transition.
Okay, well then you're on the safe side.
Yes, yes. So, but that's a little bit disappointing. It would be interesting to have. But what I think is true is that if you consider trimers, okay, like triminals, then I think you get phase transition. But I don't know much what could be computed for that. And again, if one wants to transfer both these approaches to triminals, then one has to understand why these approaches work. And that is not done. But yes, people looked at them, but they just can't see themselves.
let's thank him again. Everybody, welcome to Pogudin.